Hello, welcome back. This is Calc 1 by Dr. Oz. So today we're continuing with the Fundamental Theorem of Calculus. So this is the second video in a series of 4. And we're going to focus on understanding and using the mean value theorem for integrals and the average value of a function over a closed interval. Why don't we start? All right, before we jump into the description of the mean value theorem, I want you to think about the area between a curve and the x-axis. And remember that we used inscribed and subscribed rectangles to approximate the area by finite number of rectangles, and then eventually we passed the limit to find the actual area between the curve and the x-axis. And one observation was that if you use inscribed rectangles, the actual area is always bigger. And if you use subscribed rectangles, the actual area is smaller than the sum of those like subscribed rectangles. So the mean value theorem states that the actual area is somewhere between the inscribed and circumscribed rectangles. So like in this particular case, for example, so if you have an inscribed rectangle of this sort, as you see that the shaded region has a bigger area than this inscribed rectangle over the interval AB. And if you choose a subscribed rectangle, something like this, okay, so the area of this rectangle is obviously bigger than the area of the shaded region. So the mean value theorem says like there's supposed to be a rectangle constructed by an interior point for which you have the f of c to be the height of that rectangle. So the area of this rectangle is exactly the same as the area of the shaded region. So how nice that this whole integral here, the definite integral representing the area of the shaded region, can be written in terms of a point at which f is evaluated and corresponding to the height of the rectangle times b minus a. B minus a, as you see, is the width of this rectangle here. So for this to hold true, for this idea to hold true, we want f to be continuous on the closed interval. Otherwise, the conclusion is not going to hold true. So this theorem is only valid for continuous functions, and this theorem guarantees the existence of an interior point at which f of c, so f is calculated at c, so that becomes the height of the rectangle, and b minus a is the width of the rectangle. So whatever the rectangle that corresponds to with height f of b and width b minus a, the area of that rectangle is exactly the same as the area of the shaded region, which is in fact the area between the function and the x-axis. And notice here that this c may not be unique, okay? You may have multiple c's for which you can construct that rectangle. So in general, we're looking for one c, but it may turn out that you may have multiple c's for this equality to hold true. And here's one quick example. I want to go through that with you. Let's check this out. So you have a function 4 cosine x defined on the interval negative pi over 3 and pi over 3. And the question is asking you to find the c's, a c or c's guaranteed by the mean value theorem for integrals. Okay, so let's go back to the mean value theorem. Let's clean this up. So it says like the integral of f from a to b dx. Here we go, integral from minus pi over 3 to pi over 3 for cosine x dx is equal to f of c times b minus a. Okay, let's check that out. F of c times pi over 3 minus pi over 3. Okay? So in other words, this is equal to 2 pi over 3. I'm going to try to find c in this term here, like because you have f of c, but I need c or c's. So that this equality holds true. All right, so I rewrote this expression. As you see that I pulled out 4 here on the left-hand side, and I wrote 2 pi over 3 here as the result of that difference right here. So right now we're going to evaluate the definite integral, and all I need to find the value of that is an antiderivative of cosine x, because the first fundamental theorem says that if you know the antiderivative, if you know an antiderivative of cosine x, then you can write down the value of the definite integral by using the antiderivative. Okay, so for that reason, I need to know the antiderivative of cosine x. Here we go. The antiderivative of cosine x is just sine x. So I go ahead and put that back in the description here. I'm sorry. There we go. In fact, right here. Okay, so let me just use this. Here we go. So the antiderivative of cosine x is sine x. I'm going to use the bracket notation here. Minus pi over 3 and pi over 3. I still have 4 as a factor here. And on the right, I have 2 pi over 3 times f of c. Okay. All right. So sine x evaluated at pi over 3 minus sine x evaluated at negative pi over 3 is the result of the left-hand side. So it's 4. Let me just clean this. And continue right here. 4 times sine evaluated at the upper limit, sine pi over 3 minus sine evaluated at the lower bound should be equal to 2 pi over 3 times f of c. Okay. All right, sounds good so far. So sine pi over 3 is radical 3 over 2, and sine negative pi over 3 is negative radical 3 over 2. I try to use the exact values here because I'm going to need them. So 4 times of that equals 2 pi over 3 f of c. Okay. So let's simplify this. This minus minus becomes plus. So that's radical 3 and 4 times radical 3. 4 times radical 3 is equal to 2 pi over 3 f of c. So out of this, if you multiply both sides by 3 over 2 pi, so that's 12 radical 3 over 2 pi, which is essentially equal to 6 radical 3 over pi. Let me just write it right here. All right, so f of c is found to be 6 radical 3 over pi. You can go ahead and find c by writing what f of c is equal to. So f of c equals 4 times cosine c, and cosine c equals 6 radical 3 over 4 pi, and c comes out as, so c is going to be cosine inverse of 6 radical 3 divided by 4 pi. Okay, and you can go ahead and calculate this, but in the meantime, all I needed, in fact, was f of c. Let me just rewrite here. So f of c equals 6 radical 3 divided by pi. So if you graph the function 4 cosine x over the interval negative pi over 3 and pi over 3, you will see that this area mentioned in the problem is this orange region. And I know f of c is found to be like 6 radical 3 divided by pi. Here we go. So this line exactly. So if I make up a rectangle whose height is 6 radical 3 over pi, and the width to be exactly negative pi over 3 and pi over 3. So here, so the width is going to be 2 pi over 3 essentially, right? So the area of the rectangle is the same as the area of the shaded region, the orange region. And if you want to find the c values, you should have 2 of them, in fact. And you should have 2 of them. One of them is right here. and the other one is right here. So if you want to go ahead and use your calculator to find cosine inverse of 6 radical 3 divided by 4 pi, make sure like whatever comes out of your calculator is going to be positive, but there's also the negative version of that by looking at the graph here. So you will find two different values for which f of c is exactly equal to 6 radical 3 divided by pi. So I think that ends the question, and please go ahead and then find the value of this inverse cosine function, and the negative version of that is as well a good candidate for c. So you will have two different c values coming out of your calculator. All right, the next fact that we're going to go over, in fact, the definition in this case is the average value of a function. In the mean value theorem, we had that this definite integral is represented by f of c times b minus a. And here we're going to call this f of c as the average value, because if you just solve this equation for f of c, in other words, if you divide both sides by b minus a, as you see that 1 over b minus a times the definite integral is f of c, and we call that from this moment on to be the average value of the function. So we just state in the definition that f is integrable. In other words, this definite integral is supposed to be defined. It's supposed to exist. If it exists and if it spits out a number, that number divided by b minus a is called the average value of the function. So why don't we go ahead and solve an example here. So the question is asking to find the average value of the function 3x squared minus 2x over the interval 1 and 4. Well, let's go ahead and find it. So first of all, we need this definite integral to be evaluated, 3x squared minus 2x dx. And I'm going to multiply that by 1 over 4 minus 1. So average value, right? So all I need is the evaluation of this integral. So for that reason, I'm going to need an antiderivative of this piece here. So we're going to use the power rule for integration. So it's like 3 times x to do 2 plus 1 divided by 2 plus 1. And then, x comes with the power 1. So why don't we add 1 to the power, divide by the new power, okay? And I'm going to use the bracket notation here, 1 and 4. And then I'm going to multiply everything here by 1/3. Okay? So I'm going to just put all the parentheses and brackets and everything in order so that I won't get confused at the end. All right, so here we go. 1/3. I have 3x cubed over 3 minus 2x squared over 2 with the bracket 1/4 in parentheses. Here we go. Let's simplify this a little bit. So 1/3 x cubed minus x squared, right? Because these 3's and 2's are gone, right? And I know how to evaluate or how to understand this bracket notation. All I'm going to do here is that evaluate the antiderivative here at 4. So the antiderivative is x cubed minus x squared. So 4 cubed minus 4 squared minus, I'm going to plug in the lower limits, 1 cubed minus 1 squared. Okay. Well, this is 0. 4 cubed is 64. 4 squared is 16. And that adds up to 48, I believe. So 1/3 of 48. That takes you all the way to 16. So what that means is the average value of the function 3x squared minus 2x over the interval 1 and 4 is exactly equal to 16. And in fact, you can see that from its graph. As you see that the average value of the function, so the function in fact takes the values in between 1 and 40 here, right? 1 and 40, right? But the average value based on this description coming out of the mean value theorem for integration, the average value of the function is exactly equal to 16. And if you make up a rectangle whose height is 16, and width is 3 in this regard, right? So, and if you look at the area of that, that area should be exactly the same as the area between the curve and the x-axis. So the pink region and the area of that should be exactly equal to the area of the blue region. So that's exactly what it means to have the average value, and how we're going to look at the average value in terms of the area concept. Here is a very nice example for you to go over. The question is asking you to find the average value of the function over the interval 0 and pi over 2. All you're going to need is the definition of the average value, which is in fact, what is that? 1 over right end minus the left end of the interval, and interval from 0 to pi over 2. Cosine x dx. So all you're going to do here is to evaluate this definite integral and show that the average value is achieved, and in fact average value as the height of a rectangle times pi over 2 minus 1, which is the width of the rectangle, is the area between cosine x and the x-axis. So please go through this example after you watch this video, because it's a very nice application of what we have done. All right, so this is the end of the second video. Please watch the third video. That's going to be the next. Bye.